All right, well, I guess we'll do the introductions. So welcome everyone, or introduce everybody to Ying Cui, I hope I got that right, from the University of California, Berkeley. Her research focuses on mathematical foundation of data science and optimization techniques. In particular, leveraging non-smoothness to design efficient algorithms for large-scale nonlinear problems. In fact, she recently co-authored the monograph Modern Non-Convex Non-Differentiable Optimization. So you're throwing away a lot of nice properties there. Do what you can with what's left. And so today, Ying will be speaking to us about solving optimization problems with superquantile constraints.
Yeah, great. Thank you, Jeffrey. And I just want to make sure my internet connection is good because actually just now I was frozen a little bit. So please stop me if it doesn't really work well. So today I'm very happy to share with you my recent work on actually an optimization solver for solving a class of risk-averse stochastic optimization problems. And this is the joint work with my PhD student, Jake Ross. Actually, I started to work with Jake when I worked at the University of Minnesota. And this work, Jake is really like the driving force behind this work. And I'm glad to share this work with you today. So I want to start with the basic definition about the superquantile in case you haven't heard about that. So superquantile is actually, this is like a risk-averse metric. And that is like a very popular metric in the risk management or in the stochastic optimization. So where instead of like just caring about the expectation or the sample mean of the random variables, we care about like the tail behavior. So for example, if you give me an alpha, which is like a scalar between 0 and 1, then I would ask what is really the average of the worst 1 minus alpha % of all the outcomes. So if you look at the figures I'm drawing here, so it basically means, okay, actually I just care about average over a certain tail part. And how large is this tail? Then it depends on your value alpha. So when alpha is small, then actually it just means I cared about the very tailed behavior of this of the random variables. So then you can easily tell because I only care about the right tail, the average over the right tails. So then obviously this is like risk averse because actually I ignore all the left tails, which have relatively small values. And to give you a more specific example, so let's see, if for a very simplified case, my random variable omega follows a discrete distribution, and I just assume for simplicity that they're all like all the omega I, this kind of location, they're equally distributed. So let's say I have like m different cases, and when the probability of omega equals to omega I, if all of them just equals to 1 over m, then what is my C-var? So this superquantile. Oh, by the way, so this C-var, this is short for the conditional value at risk. So which is just actually another name of the superquantile. Then the C-var, based on our previous definition, we see we only care about the average over the tail behavior or the worst cases. So actually you need to rank or sort all the possible values of omega I from the smallest to the largest. And I only care about like a proportion of the scenarios or the cases. Like I only care about the average over those very large values of omega I. So here, when I use a square bracket as the subscript of the omega, then it means actually I'm talking about the i's. So for example, this omega I means the i's largest value over all the scenarios. So which means actually I will rank all of the omega I from the largest to the smallest, and then I care about the average over the top k largest cases. And this k, of course, it is determined by the threshold alpha you gave me, and m is the total number of different omega i's. Okay, so that's the meaning of the superquantile. And the optimization problem we are interested in is actually, well, it can take this pretty general form where in the objective function, so we have a deterministic function theta x, and just for simplicity in our current solver, so we assume this function theta is convex. And for the CVAR, for the stochastic part, so we use the CVAR instead of the usual situation where people use the expectation to measure this kind of uncertainty. So we, for example, in the objective function, if you have a random function where there are some uncertain information omega, then we just care about some worst cases over this omega. And similarly for the constraint. So whenever you have a stochastic constraint and you want to like hedge against the kind of uncertainty, then we use the CVAR, the superquantile. And each Fi, so F0 and Fi here, we all assume they are convex in terms of our decision variable X. And this is not really necessary in order for our whole numerical algorithms to work, but just for simplicity. And we plan to generalize this kind of restriction to more general situations later in the development of our algorithms. And this kind of model is actually this is absolutely not new. This kind of model is actually broadly used in many different areas. For example, like the portfolio selection in the financial industry and some operational plans. And maybe you also talk about machine learning or statistical models. So whenever you have some uncertain information in the system and you want to have a risk-averse approach or a risk-averse attitude towards this kind of uncertainty, then certainly you can use CVAR or the superquantile as one of the ways to hedge against the uncertainty. So although this kind of model actually it exists or it is known for a long time, like 40 or 50 years, but actually very recently it attracts a lot of attention from the machine learning community, which to me is very interesting because people nowadays, they really care about the fairness issue in those AI models. And it turns out this kind of CVAR, because you are hedged against the worst situations. So it turns out to be a very useful tool to deal with the fairness issue in the ML models. So that's why actually 2 years ago, I started to think about whether there is a very efficient numerical algorithms to solve such kind of problems. And before really talking about our numerical approach to solve such kind of model, I want to spend some minutes talking about really what is the difference in terms of designing numerical algorithms to solve the expectation or the risk neutral case versus the risk averse superquantile or this kind of CVAR metric. So if you think about the expectation, then what does it really mean? It just means, for example, we can use the sample average as the point estimate of the expectation. So it's just simply you take m numbers of samples and compute their average, you'll get a good approximation. But for CVAR, because this is risk averse, so you only care about those worst scenarios or worst cases. So that which means even if you have m samples, not all of them, they are useful for you to really have a good estimation of the CVAR. You only care about those samples or those scenarios omega I that give you a large value of the corresponding f. And the consequence for this kind of difference between in the definition of those two metrics is that, so for the expectation, this is like a very separable. The sample mean, this is a very separable estimation in the sense that each sample actually they contribute exactly similarly in the overall estimation of the sample mean. So, or in other words, each sample, they are actually equally important because we all give them the weight 1/m. But in CVAR, it is very different. because we only care about the tail expectation. So this is more like a binary decision. Either some scenarios, they belong to the tail that you care about, then you give a corresponding weight. Otherwise, actually, you will not include that scenarios in your estimation of the CVAR because it doesn't really belong to the tail. It may be a good situation for you. Or in other words, so this is like a very non-separable situation. You need to rank all of the scenarios omega I from the smallest to the largest, and then understand which one, actually what is the weight for each scenario. Should it be 0 or should you give a non-zero weight to that particular scenario? And this kind of difference actually has a consequence in terms of the designing of the numerical algorithms. That is, if you really want to just solve a neutral case for the expectation, then you can take an arbitrary sample or an arbitrary batch of samples to estimate its function values, for example, using the sample mean and also the subgradient, right? Because every sample, they are equally important to you. And this kind of estimation, they're actually unbiased estimation, so which can be easily proved. However, for the CVAR, the estimation of the function value in the gradient or subgradient, if it is not differentiable, actually that is not a trivial situation because for different samples, you need to first know whether it belongs to the tail or not. But whether that sample belongs to the tail or not, you need to evaluate all the scenarios or all the samples and then sort them from the largest to the smallest in order to answer these questions. And in fact, in practice, when we really use this kind of risk-averse models, this alpha is very small. So for example, maybe we only care about the top 1% of the situations. So which means actually 99% of the samples, they are not really useful for you. All of their roles is just to help you determine what is the rank for each scenarios. And after that, because as long as it doesn't belong to the right tail that you care about, you will throw this sample away. So actually, it's not easy to get a non-trivial subgradient when you just simply do sampling. And then this which means, okay, you need to evaluate a lot of this function value f at a lot of scenarios in order to understand whether a particular sample is important to you. But however, you think about the computational cost, this kind of function evaluations to get this corresponding function value at a given omega, this could be very expensive. For example, if you are familiar with the two-stage or even multi-stage stochastic models, so then this function f, it could be the recurse function for the second stage or the later stages. Then in order to evaluate this function value, you need to solve an optimization problem to get the second stage solution in order to just get this objective function, this objective value, this f at a particular scenario. This is super expensive. Or even if this is not for a two-stage model, but how about the situation if, for example, this function f, this is like a neural network, especially in those ML models. So it's very likely this f is a neural network. Then this kind of function evaluation is still not that cheap, right? You need to do a lot of like matrix vector multiplications. And in fact, even if this is just simply this function f is simply an affine function, then if you have a lot of scenarios to evaluate, this is still quite expensive because you need to do a lot of matrix vector multiplication. Okay, then it seems that, or at least till now, you may feel, then does it really mean solving a CVAR or superquantile optimization problem is more difficult or computationally more expensive compared with solving an expectation problem? Because it seems that all of this kind of function value or subgradient evaluation is very expensive. And I will try to convince you today that actually this is not the situation. We can leverage the very special structure of the CVAR to really save a lot of computational cost. Okay, so given the previous difficulty, which means actually this kind of function evaluation, the subgradient seems to be very expensive for CVAR because it's hard to get an unbiased estimation just using a very small batch of samples. Then does it mean that we should consider to reduce the total number of iterations or the number of evaluations for the function values and the subgradient? Okay, if you really, so in the numerical optimization, especially for the continuous optimization, if you want to reduce the number of evaluations, then usually, okay, the first idea came to our mind is just about, how about a second order method? So that its convergence rate is much faster than the first order method. Then the number of iterations should be much fewer compared with the first order method. However, then there is always a question mark for a second order method nowadays in the large scale optimization. That is, people always feel it could be super expensive to even formulate the Hessian matrix and then to solve the corresponding Newton equation, the linear equation. So does it really mean that, okay, if you really talk about very large scale problems, for example, deep neural networks, we need to forget about the second order method and then think about how to do a first order method. But it turns out this is really very interesting for the superquantile optimization. That is, just in this particular problem, the superquantile optimization problems, it's actually very cheap instead of expensive to formulate the Hessian matrix. Because CVAR actually suggests that we should have some sparsity in terms of the Hessian matrix. So why is that? The reason is really because in this kind of CVAR or the superquantile metric, we only care about the tail behavior, the right tail behavior. And this is only a very small proportion of all the scenarios. So although we need to evaluate all the function values over different scenarios in order to know which scenario actually belong to the tail, but after you know this information, after you do this kind of function evaluation and the sorting over all the function values, actually it is only this very small proportion of scenarios that really matters, that they will contribute a non-zero Hessian matrix or a non-zero component to the overall Hessian matrix. For most of the scenarios, actually they will not play a role at all in this kind of second order information. And this brings a kind of hidden sparsity to the problems. And in fact, that is why in the title of my talk, I say this is a kind of implicit scenario reduction. So using CVAR, actually we implicitly just pick a very small proportion of the scenarios. We don't need to consider all of them. Okay, so that's the magic of this kind of superquantile metric. Okay, but this is the intuition behind our work. And now I need to convince you that indeed mathematically we can achieve this goal, or we can design a proper second order method such that its Hessian is very structured and it's very cheap to really compute this kind of Newton direction or the second order information for solving the overall optimization problem. Okay, so I don't want to go with a very complicated situation, so I simplify the problem a lot. I just want to use this very toy example to illustrate what's really the idea behind our solver. So let's imagine we have a very simple objective function that is only linear, and we don't even have any random function or uncertain function in the objective function. And in the constraint, I only have one CVAR constraint. And the inner function is again just linear. Okay, so I know this is not a good notation because you may wonder, this ax plus b, this looks like a very deterministic function. What's even the meaning of this CVAR, the superquantile? So actually you just imagine this ax plus b gives us a vector, And each row of this vector actually represents one scenario. So which is like given in such a way. Or in other words, this omega g, the random information, is actually just this vector aj, the jth row of this matrix A, and the jth entry of the vector B. Okay, so or in other words, you think about what's really the meaning of this constraint. So it means you have ax plus b as a vector, but I only care about the several largest values over this vector, and their average has to be no larger than the given threshold R. So that's the meaning of this optimization problem. So basically speaking, it just means in our general framework, we assume that this kind of random function fx omega g is actually linear in term or affine in terms of the decision variable x. Okay, but still this problem, it could have a huge dimension because the number of rows for this ax plus b, it could be huge. Each row represents one scenario, but you may have millions of scenarios in realistic problems. So which means actually the dimension of this matrix A, which is m by n, where m is the number of scenarios, because that is the number of rows, that could be huge. And this n, this is the dimension of the decision variables, which is usually like about 1,000. Okay, so that's about the scale of this optimization problem. And think about for such a scale of optimization problems, and of course, this is like a convex optimization problems. So how can we use a second order method that is still memory efficient and also computationally efficient to solve the overall optimization problem? Okay, and here is the trick we use. So actually we go with a pretty standard second order method called the augmented Lagrangian method to deal with this kind of superquantile constraints. But we play an important trick here. That is, we actually introduce an auxiliary variable y to replace ax plus b inside of this CVAR operator, and then we split the two steps actually into two parts. One is just in terms of CVAR, and another one is about this y, this newly introduced y has to be the same as the original like stochastic or uncertain function, random function. Okay, so this CVAR of this y, of this vector y, it actually just means, so although this y looks like deterministic, but the way to interpret this operator is, this is actually, you give me a vector y, and I consider the average over several, like this is a number. This notation is like a bracket, just means it's like the largest integer not exceeding this number. So this is just like give me an integer, okay, depending on the value of alpha you care about. So this is like the average of those several largest components of this vector y. And this value has to be no larger than a given threshold R. Okay, so you may wonder, why do we want to introduce an auxiliary variable to split this random function ax plus b in the CVAR operator? The reason is then I can consider just a partial augmented Lagrangian function by penalizing this kind of linear equation. And this CVAR constraint, I will just keep it in the constraint. So I will not touch it because I hope I can leverage this part to provide us a very structured Hessian matrix. Okay, so the left-hand side here, this is like the standard augmented Lagrangian function, but this is only partial with respect to the linear constraint. And then the augmented Lagrangian subproblem. So this is again standard. It just means, okay, it'll fix the multiplier lambda, which I write as lambda tilde here within the box. Then I need to solve the corresponding primal variables, x and y. And how to solve it? Well, it's an interesting observation that actually it's not difficult to really get an optimal solution y here. The reason is because you can always complete the square of the left-hand side. And if you complete the square, you will actually rewrite this kind of function as just like a square term in terms of y. And because you have another constraint, the superquantile constraint for y, then the optimal solution of y in my left box actually must be the projection of this kind of CVAR constraint. So the Euclidean projection onto this CVAR quantile ball. Okay, and if knowing the optimal solution for y, it means actually I can eliminate this y so that I get another optimization problem just in terms of x. Okay, which in other words, actually, I don't really lift the original problem into a higher dimension. So this y, this is just like an intermediate step here, help me to get a relatively nice augmented Lagrangian cell problem. And why do I see the objective function in the red box? Why this is nice? The reason is because now this is an unconstrained optimization problem. And what is even better about this optimization problem is that actually it can be proved that the orange part, this square term, is actually, although it looks complicated, it involves a projection onto the CVAR constraint, this kind of level set constraint. But actually the whole square term here is actually continuously differentiable because this is actually a distance function. A square distance function. Okay, and the distance is with respect to this CVAR constraint. Okay, so okay, if you don't know, so well, it is okay if you don't know why this is continuously differentiable, but well, trust me, this is like a differentiable situation. And another good thing about a differentiable function is now, in order to solve this optimization problem, all I need to do is to make its gradient equals to 0, because this is a convex optimization problem. I only need to solve the first order optimality condition in order to get an optimal solution. Okay, so then I take the gradient of the whole objective function, and because of this, there's no other constraint, so I just need this gradient. So this will be the corresponding gradient of the objective in my box, and then I just need to set this gradient equals to 0. Okay, so then it means it actually all I need to do in order to use the augmented Lagrangian method to solve the superquantile constraint problem is to know how to solve this equation in terms of x. But this equation, it doesn't look that nice anymore. The reason is because there is actually involves this projection operator. And this projection operator, this is actually a very nonlinear operator. And which means actually you need to know how to solve this nonlinear equation efficiently. And especially considering the situation, considering the fact that this matrix A may of very large scale, like it can have millions of rows, whether you can still solve this kind of nonlinear equation very efficiently. That's a big problem that we need to solve. Okay, but what is not that bad about this projection operator is, although this kind of projection is not a smooth operator, this is no longer continuously differentiable anymore, but this is actually piecewise smooth, which means actually I have a piecewise smooth equation to solve. And in order to solve a piecewise smooth equation, actually there is a pretty standard method in the optimization literature. That is just to use the semismooth Newton method. So the semismooth Newton method, if you don't know the detail, actually you just take it, you just imagine this is almost the same as the Newton method to solve a smooth nonlinear equation, where at each step you just linearize the whole equation and get the direction to move. So the only difference is that because now this is no longer differentiable, so you can now really take the Jacobian of this kind of equation and apply the Newton's method. Then we have, in optimization, we have a way to define the generalized Jacobian, and then you can still go with exactly the same way. Okay, so, or in other words, it's still like each step, you just do a linearization of this equation. And the net linearization, because you take the Jacobian of this equation, it is more like you consider the Hessian of the original problem, because this equation is already the gradient of the original objective. So if you consider like one more gradient or one more Jacobian, then it's like the second order information of the original objective function. Okay, so which means actually there is no issue. We just need to apply the semismooth Newton method. But is it efficient to deal with very large scale problems? And then actually we need to work very carefully about this kind of nonlinear equation and think about what's really the generalized Jacobian of this kind of nonlinear function. So actually the first question, even before talking about the Jacobian, the first question about this nonlinear equation is whether I can evaluate this kind of projection very efficiently. Because this projection itself may already be difficult to deal with. So what's really the meaning of this projection? A projection means, okay, I give you input vector y0, which actually will be this whole term in my algorithms. Okay, but just imagine if you give me an input vector y0, I need to solve this optimization problem in order to compute the projection. And the optimal solution y will be the corresponding projection. So what's the meaning of this optimization problem? That is, I want to minimize the distance of my y with respect to the input vector y0 and satisfying this kind of CVAR constraint. And because this CVAR constraint actually restrict the sum of or the average of the top k components of my vector y. So actually it is equivalent, it can be equivalent written in such a way where again, this kind of y, the square bracket of 1, it just means the largest entry of the vector y. Okay, so or in other words, yeah, it is what I'm writing on the right. So that is actually you need to sort all the components of y from the largest to the smallest, and then consider the threshold to a certain threshold. Okay, so this optimization itself seems to not be very easy to solve, but actually there is a trick to play here. That is, you can easily imagine the optimal solution y. It must follow the same so it must follow the same order, all its component with respect to y0. Or in other words, like if your y0, you know it's sorting, which I just denote, I use a down arrow to denote the sorted value or the sorted vector of my input vector y0. So which means actually first you give me an input vector y0 and I just do the sorting of all the components from the largest to the smallest. And I can prove that if you sort your y0 input vector, then my solution of this optimization problem, it must follow the same order, which means I have this kind of isotonic constraint of all of its components. Or in other words, then I can equivalently written my projection problem into the optimization problem in the bottom. That is, I add another sorting constraint or isotonic constraint. And then, because now if you add this kind of isotonic constraint, you know which one is the largest. So the largest y will be, it must be this y1, right? So which means actually this kind of the original constraint, it just boils down to you consider the sum of the first k components of y, and you give a bound on their summation. Okay, so and now I like this optimization problem more because this is like a very standard, strongly convex quadratic optimization problem. But still, the issue is this problem, it can have very large scale. Your M could be millions. And if you just call like Gerby or whatever like existing solver to solve this problem, it may not be very efficient. Okay, so then we think about how to really solve this projection problem. And I may quickly skip this part because actually we do a separate paper on this particular problem. And the main idea is it turns out in order to solve this projection problem, to get this projection, all you need to do is to do a partition of the input vector y after sorting into 3 parts. So the first several parts, actually you will do a translation. So each of them, you will move by a same amount because you want to guarantee that their summation is not too large. And then in the second partition, in the second set, actually all of those elements, you will move them to the same value. That is exactly the case largest value. And then for the rest, you will maintain the same value. Okay, so this part, this is like a pretty technical part, and I don't want to go into much details about this part, but the main message I want to say is that it turns out actually we can design a linearly scaled algorithms, a very, very specific algorithm to just solve this projection problem. Yes, but if you use any like existing solver based on the interior point method, it will scale cubically in terms of M. So it will be of the order capital O M cube, and that's a lot. We cannot afford that kind of computational cost. But because of the very special property of the CVAR, actually we can design a very specialized algorithm that is linearly scalable. Okay, so here I just want to show you some numerical evidence about how efficient this very specific linearly scaled algorithm to solve this, just this projection part. This is not the whole optimization problem. Okay, so we compare our particular algorithm with the Gorby, the Gorby solver to solve this projection problem. And now you can see if the problem is not of very large scale, see this dimension is just about 1,000, then actually Gorby does a pretty good job. So actually it can solve very efficiently. So the this number there, the computational time that it takes to solve the problem. And the value within the bracket, it means the standard deviation. So actually we repeat the experiment like 100 times for different simulations, synthetic data. Okay, so maybe you just ignore the numbers in the bracket and look at the, like all the like 3.1 times 10 to the power minus 3. So this means the computational time it takes for the Gorby to solve the case where M is about 1,000. But you can see that if we really scale to like 10 million, then it takes Gorby a quite long time. Actually, it cannot be solved within 10 to the power 4 seconds. But for our algorithm, it just takes about 0.2 seconds to solve the whole problem. So that's almost nothing, and it's pretty cheap. Okay, so which I hope I can convince you that just this projection part itself is not that expensive to really do the computation. Okay, now let's go back to the original problem. The key idea I want to convey is that, or to talk about is that how to really solve this kind of nonlinear equation very efficiently. So the previous part, again, is just about how to really compute this projection. But now in order to solve this equation using the semismooth Newton method, just like the Newton method, I need to linearize this function, capital F, this map, which is the so-called general Jacobian, because I can now really take the derivative or the Jacobian. Okay, so what's really the general Jacobian of this capital F? Then you think about the first part. So the first term involves x is this linear function. So which is easy. I know its Jacobian must be like A transpose A. So which gives me the first part, like A transpose the identity matrix times A. And the next part involving x, my decision variable, that is this whole projection part. So based on the chain rule, then I need to first derive the general Jacobian of this projection, which is actually the matrix J here. This matrix J is just the general Jacobian from the projection part. And then based on the chain rule, I also need to multiply the matrix A. And also there is another A transpose here. So putting it together, this is how the general Jacobian looks like for the whole function capital F. Okay, but then what is really this matrix? Is this one efficiently to compute? And again, I want to remind you, this M, it means the number of scenarios or the number of rows I have for the matrix A. and it could be very large. It usually has the order like millions. Okay, and then I must have a very efficient way to even compute or store this whole matrix A transpose I minus J times A, even if this M is huge. But you can imagine this kind of, if you just use very naive matrix multiplication, the computational cost, it will be a lot. It will be like squarely scaled in terms of M, which is absolutely not acceptable. But if you really look into the detail about how this middle part looks like, because we know this J is the Jacobian of this projection, and because of the very special property of this kind of projection, so you can imagine for the projection part, so every index belongs to my third set on the left. So actually, this is more like is after its projection, it remains the same. So its Jacobian it must be like the identity matrix. And then you have another identity matrix before in front of it. So this identity matrix minus that identity matrix part, you will have a huge zero in the whole middle part. And how large is this part? How large is this zero? Actually, it will be similar to just like the number of non-effective scenarios. Or in other words, as long as that scenario doesn't belong to the right tail that you really care about, the worst scenario that you care about, it will actually just give you a zero Jacobian in your second information. So the only non-trivial part in the middle of this I minus J is only this red corner, and which is in fact, roughly speaking, it is just about the size of the effective scenarios. That is indeed those scenarios belong to the tail, the right tail that you care about. So that's much, much, much smaller than the whole M. So, or in other words, actually you only need to care about those effective scenarios in the second order information. Okay, so this is the key reason why we can have a very efficient computational procedure to solve this nonlinear equation. Okay, so how do we really compute this matrix product? Actually, we will not just do the matrix product one by one. First, do the multiplication of this A transpose with I minus G, and then multiply by A. That is too computationally costly. We will simply just divide this I minus J into two parts, and then construct another matrix A tilde. And this A tilde is of a much smaller size. So this size, it is about the size of the right tail. So usually this is just like 1 minus alpha proportion over all the scenarios. And that computational cost is much, much smaller than the naive implementation of this kind of three matrix multiplication. Okay, and here I want to really show you really what is the computational cost for the gradient and then the Newton and the Hessian information. So the gradient evaluation, so the meaning of the gradient evaluation is just how you compute, or what is the computational cost to evaluate this function f, because this capital F is already the gradient of the original objective function in my augmented Lagrangian subproblem. And that one, actually, because you need to do the sorting in order to get this projection operator. So there is like an m times log m computational cost in terms of the sorting part. And then because it involves some matrix vector multiplication, and this kind of matrix A multiply the vector X, so because the matrix A has the dimension m times n, now the computational cost will be m times n. So you can see actually this gradient evaluation is not that cheap. It scales at least linearly, actually a little bit more than linearly in terms of m. So it's really not that cheap. However, if you further compute the Jacobian of this function f, which is what I'm saying about the Newton equations here, this computational cost, because now I only care about the scenarios belong to the right tail. That computational cost is actually independent of this value of M, the number of scenarios. It only depends on a very small proportion. So this part, it just means a very small number of critical scenarios of my whole evaluation. And this kind of independence of M, this is really critical. Or in other words, actually, it really suggests the computational cost in terms of this kind of second order information is in fact much, much cheaper because it is independent of M. So that is much cheaper than the computational cost to get the first order information, the gradient, this kind of gradient evaluation. And which means actually it seems that we can get a conclusion that is this CVAR operator itself, or this kind of risk averse operator itself, help us to do a scenario reduction because it helps us to select the important scenarios in terms of the computation. And of course, this kind of scenario reduction or scenario selection, this is like an implicit way because it also depends on at the current point, like what is your value of X, so that you will get the whole evaluation of the term inside of the bracket to determine which scenario to include and which scenario to exclude. So you cannot predetermine it before you really solve the optimization problem. That is why we see actually the CVAR is a kind of implicit scenario reduction. Okay, so it seems that I spent too much time. Then just 1 minute, I want to show you some numerical experiment. So we compare with the first order method. This OSQP is like a first order implementation of the, it's an implementation of the first order method, ADMM, to solve the convex optimization problems, the quadratic optimization problems. And you can see we can, even for a very low accurate solution, which usually people think the first order method should be good at. And actually we are like about 600 or 400 faster than it. Okay. And if you want to get a relatively high accurate solution, for example, the accuracy is about 10 to the power minus 6, then actually we need to use some second order based solver like a Gorby. And we compare with Gorby and also another commercial solver portfolio, the Safeguard. So this PSG, this is like a very tailored implementation of the Gorby and other like SQP solvers to solve the risk averse optimization problems. And we compare with these two methods. And now you can see like for example, for the problem of this scale where M is 10 to the power 5, then the computational cost, you look at the last column, 3 columns. For our ALM, this is the algorithm we propose. We just need within like half minute to solve this optimization problem. But it takes Gorby a long time. It's like more than 200 seconds to solve it. For PSG, although it seems that it is very fast, like it just takes it 20 minutes, but actually it doesn't really get a primal feasible solution. So you can see, you can focus on the second column and see actually the primal infeasibility. This is very bad for the PSG. So actually it doesn't really return us a good quality of the solution. And for the other situations, actually PSG is no longer that stable. Actually, it takes more than 1,000 seconds to solve it. But still, like for our algorithms, it always like it is very stable and scalable. So it just takes no more than half minute to solve the problem of this scale. And if you really look at the breakdown of the time spent on the first order gradient evaluation and the second order Newton evaluation, you can see actually the time spent for the Newtons to solve the Newton equation, to formulate and solve the Newton equation, that is even cheaper than just to evaluate those gradients. So which really suggests that this kind of CVAR is very in favor of the second order method to solve it. And again, that actually is consistent with our theoretical computational cost. The gradient evaluation actually, it scales linearly in terms of, at least linearly in terms of M, but the second order information, the Newton equation, its computational cost is independent of M. So that is why our algorithm is so scalable in terms of M. Okay, so this is like the idea of our solver. So our solver is implemented in Julia, and that is available on my webpage and also available on my student Jake Ross webpage, I think. So we only support this kind of form. That is, basically speaking, it has to be convex. But in the near future, actually, we want to just add more features, especially adding some non-convex functions, in particular neural networks, so that it can be more broadly applicable. And also we want to think about, like, if there's like a two-stage or multi-stage stochastic optimization, then how to incorporate the CVAR into the model to help save the computational cost. Okay, so that's all for my talk. And so it is based on those two papers. And also the link of the code is they are available within this paper. So if you're interested, maybe you can take a look. And that's all for my talk. Thank you very much.